All around us, on literally every single object you can see and touch, there's this invisible world of chemistry just happening. It's kind of like a secret science, one that's purifying our water, cleaning our air, and, get this, even helping feed the entire planet. So today, we're going to pull back the curtain and uncover the hidden power of surfaces.
So let's start with a really simple question. We've all seen charcoal in a water filter, right? But have you ever stopped to wonder how this black, porous rock actually pulls all that gunk out of the water? Well, the answer isn't magic. It's a really fundamental principle of surface chemistry.
You see, that piece of charcoal, and actually most surfaces, have a kind of superpower. It's a process called adsorption. And believe me, it is the key to pretty much everything we're about to dive into. At its heart, it's actually remarkably simple. Just think of a surface as being, well, molecularly sticky. It has this amazing ability to attract molecules that are just floating around in a gas or a liquid and then make them cling right to it. It just plucks them right out of their environment.
Okay, so let's get the official lingo down, just so we're all on the same page. The process is called adsorption. And yeah, I'm really emphasizing that D sound, adsorption. It's super easy to mix up with absorption, but they're totally different. Absorption is when something gets soaked up all the way through, like a sponge soaking up water. Adsorption, that's strictly a surface thing. The molecules just stick to the outside. So the surface that's doing the grabbing, in our case the charcoal, that's the adsorbent. And the stuff getting grabbed, those impurities in the water, that's the adsorbate. Simple, right?
All right, let's move on. I like to call this next part molecular Velcro, because this molecular stickiness isn't some one-size-fits-all deal. As you can see, not all sticking is the same. There are definitely different strengths for different jobs.
So this Velcro really comes in two main types. First up, you've got physisorption. This is a pretty weak, temporary attraction. It's driven by these faint, short-range electrical forces between molecules. The best way to think about it is like static cling. The molecules are stuck, but you could remove them pretty easily. But then there's chemisorption, and this is the real deal. This is a super strong attraction where actual chemical bonds are formed between the surface and the molecule. So forget static cling, this is more like superglue.
And here's a really cool detail. That super strong chemisorption bond, it doesn't just happen instantly. It's almost always kicked off by the weaker physisorption first. So a molecule is kind of drawn in by that gentle static cling, and then, once it gets close enough, bam, the stronger chemical bond can form.
So far, we've only talked about how surfaces can just grab molecules. But the really powerful surfaces, they do so much more than just hold on. They can actually transform them. This is where a simple surface levels up and becomes a miniature chemical factory. And that whole process is known as catalysis. We're talking specifically about something called heterogeneous catalysis. Now, I know that sounds like a mouthful, but it just means our catalyst, the surface, is a solid, while the things it's reacting with are gases or liquids. And the critical thing to remember is this. The surface acts like a platform, a sort of molecular meeting place that dramatically speeds up a chemical reaction without ever getting used up itself.
The whole thing works like a tiny, incredibly fast assembly line. First, the reactants arrive and get adsorbed onto the surface. Second, the surface helps weaken their existing bonds and encourages them to rearrange into something new. Third, the new product is created. And finally, and this part is absolutely key, the new product detaches or desorbs, which frees up the surface to do it all over again, literally millions of times per second. It's amazing.
So where can you actually see this incredible process in action, like every single day? Well, you don't have to look much further than the catalytic converter that's in pretty much every car on the road today.
Think about it. A car's engine, it produces some really nasty stuff. We're talking toxic carbon monoxide, smog-forming nitrogen oxides, and unburnt fuel. These are the reactants that are heading straight into our catalytic factory.
So inside that converter, there's this honeycomb structure, and it's coated with a super thin layer of precious metals, things like platinum, palladium, and rhodium. That is our catalyst surface. As those toxic gases pass over it, they get adsorbed, they're rearranged, and then they're desorbed as completely harmless substances, carbon dioxide, nitrogen gas, and plain old water. The efficiency here is just staggering. We're talking over 99% of pollutants get completely neutralized.
Okay, so for our last section, let's see how these surfaces really do change the world. Because this technology, it goes so far beyond just cleaning up car exhaust. This secret science is basically a pillar of our modern world, and it has a huge impact in a field you might not expect, agriculture.
Let me introduce you to the Haber-Bosch process. It uses a specially designed catalyst, usually iron-based, to do something that should be impossible. It grabs inert nitrogen gas right out of the air we breathe and combines it with hydrogen to create ammonia. Why does that matter? Well, ammonia is the single most important ingredient in modern fertilizers. Now, it's a super energy-intensive process, which is why chemists are always on the hunt for even better catalysts to make it more efficient.
Just look at that number. That's not 120,000. It's 120 million tons every single year. That's how much ammonia we're making with this one catalytic process. And it is absolutely no exaggeration to say that this single application of surface chemistry is what's feeding billions with a B, of people on our planet right now. It's mind-boggling when you think about it.
So, here's the bottom line. From the simple charcoal in your water filter to the converter in your car, all the way to the fertilizer that grew the food on your plate, the secret science of surfaces is absolutely everywhere. It's the hidden engine of the modern world, enabling all this technology that keeps us safe, healthy, and fed. Which, of course, leaves us with one final thought. We've really just scratched the surface today. No pun intended. But if this invisible chemistry can have such a profound impact, turning pollution into clean air and thin air into food, what else is it doing? What other secrets are hiding in plain sight on all the surfaces around us, just waiting for us to understand them?